Hi everybody. In today's lecture, I'd like to talk to you about collisions. So, a collision is a term that we use to represent an event during which two particles or more particles come close to each other and then interact by means of forces. Now, they can involve physical contact, like I'm going to do some examples today that do about car collisions and billiard balls. But the ideas that I'm talking about today can also be generalized to include cases that have some kind of interaction without a physical contact. And really on the nanoscale, what does it even mean when you say two particles are touching, right? Now, we're going to make certain assumptions. First is that the time interval during which the velocity changes from its initial and final values is assumed to be a short period of time. Now, it is true that what we mean by short could change depending upon what two bodies that we're talking about. If we're talking about high energy particles, then maybe those high energy subatomic particles are like picoseconds or femtoseconds for the collision. Whereas if you're talking about large objects having some collision, you might be talking about, I don't know, a tenth of a second or something for the collision to occur. Or for astronomical bodies, maybe a really long time. But it's in comparison to the length of time for the motion of the system in question, and I hope that helps. Now, we're also going to assume that the interaction forces are a lot greater than any other external forces present, so we can use the idea of impulse in the collisions. Now, if there are external forces which are actually, a significant fraction, then what you can do is a little bit of a dance where you consider only just before and just after the collision. And then from there, just after the collision, you can have those other external forces kick back in again. Okay? So, those are some tricks that you can use. All right, so like I said, collisions can be the result of direct contact. The impulse forces can vary in time in complicated ways, but in the examples that we're going to use today, we're going to assume that there's some average force that acts throughout the collision. In all collisions, momentum is conserved, and that's because of the assumption that we made on the previous page that the forces at play during the collision kind of dominate over any other external forces that might be present. And so if the F external is close to 0 or 0, then F is equal to 0 is equal to dp dt, and then P initial equals P final. Momentum is conserved. Okay? So that's the assumption that we're going to make. Now here's a little sketch of a collision that doesn't actually have to involve physical contact. So here we see a proton and a helium nucleus, right? And they come very close to one another, and they interact with these strong Coulomb forces. But because the Coulomb force is so strong, they don't actually touch one another, okay? And so that they don't have to involve physical contact, in other words. But we can use the same ideas for momentum conservation to figure out this collision that we use for ones where you do have physical contact. Now we're going to talk about different kinds of collisions. There's different classes of collisions. There's elastic collisions and there's inelastic collisions. Now in inelastic collisions, kinetic energy is not conserved. But of course momentum is conserved. It's conserved for all collisions. Now, there's also a subclass of inelastic collisions called a perfectly inelastic collision. And a perfectly inelastic collision, the objects that collide then stick together during the collision, and you have this big mass, single mass moving away in a perfectly inelastic collision. Now there's also elastic collisions. In an elastic collision, both momentum and kinetic energy of the system are conserved. Now, I want to stress that it's the momentum is conserved for the system as a whole and the kinetic energy of the system as a whole. Of course, if you have, for example, a fast object colliding with a stationary object, for example, then even if kinetic energy is conserved, the fast one's going to lose kinetic energy and the one that was stationary is going to gain it. Okay, so it's for the system as a whole that these things are conserved. The individual momenta and kinetic energies of the constituents can be, transferred to another. So here's a simple example of a perfectly inelastic collision of two bodies, M1 and M2, with initial velocities V1 initial and V2 initial. sticking together after the collision and then moving off at some final velocity. And so, of course, momentum is a vector, so this is a vector equation, and you would set the momentum initially for the system equal to the final momentum of the system. For a perfectly inelastic collision, that would be m1 v1 initial plus m2 v2 initial is equal to m1 plus m2 times v final. Okay, and then both objects would have the same final velocity because they're stuck together. So I wanted to do an example problem for you, kind of one of those blood runs red on the highway examples of a perfectly inelastic collision. And in it is subtext for you all to be very safe drivers. Okay, so here we go. Two drivers, each of 80 kilograms, are driving a dump truck and a subcompact car. They collide head-on in a perfectly inelastic collision. Each vehicle was initially moving at 8 meters per second. The mass of the car is 800 kilograms and the mass of the truck is 4,000 kilograms. If the collision time is 0.12 seconds, what force does the seatbelt exert on each driver? Okay? Now, for all of these problems, it really helps to draw yourselves a picture first. So I draw pictures of the initial condition and the final condition. You don't have to be Rembrandt or anything. Just simple little sketches are fine. When I draw my sketch, I choose my origin, my coordinate system, and then assign variable names to anything that I might not have a value for. So here's the sketch up here at top right. I've got my big truck, symbolized by a larger square, and it's going to be traveling to the right here, and I've got my little subcompact car as the smaller rectangle, and it's traveling left. So this is my initial up top, and then final down bottom. It's a perfectly inelastic collision, so they're stuck together. So I represented that by this funky looking ticket shape here, and they're going to be traveling to the right probably because the dump truck is a lot bigger than the subcompact car, so it'll probably win the day. But if I drew it wrong, okay, it's no big deal. It'll get solved for when I do my algebra. Okay, so the next step after drawing your picture is to write down the initial and the final momenta of the system. Now, you might not be able to put numbers in for everything right away. That's okay. You just sub in variable names for anything that you don't know. Okay? Now, remember, our perfectly inelastic collision equations look like this. M1 V1 initial plus M2 V initial is going to equal to M1 plus M2 V final. Okay? So that's what I'm going to do. I'm going to use that equation and then sub in numbers that we have for our particular problem. So my P initial, my initial momentum of the system, is going to be the mass of the dump truck and the dump truck driver, which sums to 4,080 kilograms, times the velocity for that one, which is 8 meters per second in the I hat. So I'm choosing the x direction here as my motion line here for this. And then the momentum for the subcompact car, the mass of the car and the driver is 880 kilograms, and then the velocity is in the is minus 8 meters per second in the I hat. In other words, it's going in the negative x direction. So when I sum those two things together, 4080 times 8 in the I hat minus 880 times 8 in the I hat, I get 25,600 kilograms meters per second in the I hat. So that's the initial momentum of the system. Now that's going to equal the final momentum of the system. The final momentum of the system is M1 plus M2 times V final. So that's 4080 plus 880 kilograms times V final. Okay? Now I don't know V final. I've got to solve for it. So I just represented it algebraically here. All right, so setting these two things equal, I'm going to have 25,600 kilograms meters per second in the I hat is equal to 4080 plus 880 times V final. Solving for V final, I'll divide through by 4080 plus 880 on both sides of the equation. So I have 25,600 divided by 4080 plus 880, and that gives me 5.16 meters per second in the I hat. Okay, so that's the final velocity of this big mess that's traveling to the right here. Now, this question is a little bit more about a little bit more than just momentum conservation during a collision. They also want to know about the force of the seatbelt on each driver. So you have to remember back to some physics that we already discussed and remember the equations for the impulse. The impulse is equal to the change in the momentum, which is equal to the average force experienced during a collision times delta t, the time interval over which the collision occurs. Okay, so let's do that for each driver. So the truck driver first, the driver is 80 kilograms, and so his change in momentum would be 80 times 5.16 meters per second in the I-hat minus 80 times 8 meters per second in the I-hat, P final minus P initial. And then that will equal to F average times delta T. Delta T, as given in the problem, was 0.12 seconds. So then you can solve for F average by dividing through by 0.12 seconds on each side. And when I do that, I end up with F average of negative 1,893 newtons in the I-hat direction. So the negative sign just means that the force is experienced to the left, right? So in other words, the seat belt is going to keep him in his truck. It's going to point to the left. The force is pointing to the left. And if you solve for what that is in terms of the number of G's, because oftentimes we don't really have much of a concept for what a force in newtons really means. And sometimes it's helpful to put it in the context of how much force gravity exerts on a person. So if you divide that 1,893 by mg, which would be 80 kilograms times 9.8, then you see that the force that the driver of the truck experiences is about 2.4 times the force of gravity on the driver. Now that might be a little unpleasant for a split second, but it's livable. You can definitely live through that. Now let's look at what happens to the driver of the subcompact car. Yet again, we're going to use the impulse equation, so delta P is going to be equal to F average times delta T. Now, solving for the car driver, what we're going to get, if we factor out the 80 kilograms times V final minus V initial would be the change in momentum, which would be 80 kilograms times 5.16 meters per second in the I-hat, minus 8 meters per second in the I-hat, because remember, initially the driver was traveling to the left, which is minus 8, right? So that means that it's 80 times 5.16 plus 8 meters per second, right, divided by 0.12 seconds. And that gives an average force of 8,773 newtons in the I-hat. Now, if you solve for that in terms of the number of G's experienced, then it's 11.2 times the force of gravity on the driver. So if that occurs over a very short time span, you might not live through that, okay? So this is a little warning to you to be cautious in your driving. Okay, so now let's talk about elastic collisions. In an elastic collision, both momentum and kinetic energy are conserved. And so that means that you have two sets of equations in order to solve a problem. So you have your momentum conservation, just like we did before, where m1 v1 initial plus m2 v2 initial has to equal m1 v1 final plus m2 v2 final. And of course that could be expanded if you have more elements involved in your collision. You just keep tacking on m1s and v1s, right? You just keep tacking them on. And then also you're going to have kinetic energy conservation. Now remember, momentum's a vector and kinetic energy is a scalar. So what you're going to plug in here is 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared, which is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Now remember here, this v1 initial squared, that's the speed squared. Okay, another way to think of it is the dot product of v1 with itself. Okay, so v1 initial dot v1 initial gives you v1 initial squared. All right? Let's do an example problem of that. So here I'm going to talk about billiard balls. All right, so we have two billiard balls of equal mass approaching each other. Ball 1 is moving east with a speed of 10 meters per second, and ball 2 is moving west with a speed of 5 meters per second. After the elastic collision, what are the speeds of the balls if one ball moves north and ball 2 moves south of east at an unspecified angle? Okay, so let's do this. All right, so we're going to have both momentum and energy conservation in this problem. Yet again, I've drawn myself a little sketch. So up top here, I've got the initial condition where ball 1 is moving to the right, which is east here, and ball 2 is moving to the left, which is west. I'm going to take north-south as up-down on the slide. Okay, so here I've got in the final condition, one of the balls is moving north, which points up on the slide here, and one of the balls is moving south of east, as shown here. And there's some unknown angle theta with respect to east that it's heading downwards, and we can solve for that, and I'll show you. Okay, so here we go. the initial setup is the same. You draw your picture, you use momentum conservation, solve for the initial momentum, solve for the final momentum, set them equal. Here we go. P initial is m times 10 meters per second in the I hat minus m times 5 meters per second in the I hat. Remember, west is going to be the negative x direction. And so when I sum those two things together, that gives me a total initial momentum of m times 5 meters per second in the I hat. Note that I'm using m because they didn't give me the mass of the billiard balls. But I am going to assume that all billiard balls have roughly the same mass because I've played pool before and I know that, okay? All right, so now we're going to solve for the final momentum of the system. And we're going to say that one of the balls is traveling north, so that's m times vf1 in the j hat. I've taken the y direction here to be north-south. So mv final 1 in the j hat. Now, the other one is traveling south of east. So I'm going to break their its velocity into two components. M times v final 2, the x component of that in the I hat, plus m times v final 2, the y in the j hat. Okay? Now, I don't know what any of the final velocities are, so I've left it in this kind of symbolic form. All right? Now, the nice thing here is that we have x and y components, and those are going to be conserved separately. So I can take them into separate equations. Looking at the x components first, my initial momentum is all in the x direction. So that's m v times 5 meters per second is going to equal to, now looking at the final momentum, there's only one term that's in the x direction, and that's m times v final 2 in the x. So I'm going to set m times 5 meters per second is equal to m times v final 2 in the x. Since the m appears on both sides of the equation, I can cancel out. And what that means is that the final velocity of ball 2 in the x direction is going to be 5 meters per second. So I've got one component solved for. Now, if I look at the y components, I've got no initial momentum in the y direction, so my initial y momentum is 0, and then that's going to equal to m v final 1 plus m v final 2 in the y. Okay, so there it is. Now, I can cancel out my mass, right, and that gives me that v final 1 is equal to minus v final 2 in the y direction. So the y components are going to be, equal but opposite for these two balls. All right? So I still have a couple of unknowns here, but luckily I have my kinetic energy equations, and I can use those to finish solving this problem. So my kinetic energy conservation equations are going to be the initial kinetic energy has to equal to the final kinetic energy of the system as a whole. So my initial kinetic energy is going to be 1/2 times the mass times 10 meters per second squared, plus 1/2 times the mass times 5 meters per second squared. All right, I don't know the m's, but it probably won't matter. It'll probably cancel out, so let's just go with that. So now K final, okay, we don't know either of the speeds yet, so 1/2 times m times v final 1 squared plus 1/2 times m times v final 2 squared, all right? Now what I can do is, since ball 2 has x and y components, then I can sub in there. I know that v final 2 squared is going to be equal to the sum of the squares of its components, which would be v final 2 x squared plus v final 2 y squared. That comes from the Pythagorean theorem. So I can sub in here for that 1/2 m v final 2 squared and get my final kinetic energy is 1/2 m v final 1 squared plus 1/2 m times v final 2 in the x squared plus 1/2 times m times v final 2 in the y squared. Now, if I set my kinetic energy initial and my kinetic energy final equal to one another, the m's and the 1/2s cancel out everywhere. So that leaves me 10 squared plus 5 squared is equal to v final 1 squared plus v final 2x squared plus v final 2y squared. All right? Now I'm going to use what I had from my momentum conservation equations on the previous slide. Specifically, 5 meters per second is equal to v final 2x, and v final 1 is equal to minus v final 2 in the y. So if I plug in for that, okay, I'm going to be able to solve for v final 1. So if I sub in that v final 2 in the y is equal to minus v final 1, then that would give me minus v final 1 squared, which is v final 1 squared. And that means that I have 2 v final 1 squared on the right-hand side here. And then v final 2 in the x, that's just 5 meters per second. So what I end up with is 10 squared plus 5 squared equals 2 times v final 1 squared plus 5 squared. Okay? The 5 squareds cancel out on both sides. Then I solve for v final 1, and I get that it's 10 squared, which is 100, divided by 2, and then I take the square root of that, and that gives me 7.07 meters per second. So I've got the final speed of ball 1 solved for, all right? Okay, so I can write down here, V final 1 is going to be 7.07 meters per second in the J hat, okay? So that means that it's going 7.07 meters per second north, okay? Now, what I can do at this point is I have V final 2. V final 2, I know the x component is 5, and I know that the y component is negative of V final 1, which means that it's going minus 7.07 meters per second in the j hat. So now I have both of the velocities for either of those things. If I wanted to solve for the angle theta, theta would be equal to the inverse tangent of the y component over the x component, which is the inverse tangent of 7.07 over 5. And when I solve for that in degrees, I end up with 54.7 degrees for theta. So now I have everything. I have the velocities of both balls, and I have the angle that it makes with that horizontal axis. Okay, so I'm done. All right, well, I hope you understood that and were able to follow it. As always, let me know if you have any questions, and I'll see you in class.